The double slit is replaced by a diffraction grating that has 600 lines per millimeter, right? Or 6,000 lines per centimeter, right? Which is, that's fairly typical, right? The resulting pattern on the screen is shown, okay? Satan explained the differences between the pattern on the screen due to the grating and the pattern due to the double slit, okay? Notice the things you want to notice, right? First is that it doesn't drop off, and that's because basically there's such a small distance between these slits in that grating that the diffraction pattern is really quite wide. Okay, so it doesn't drop off like that. That's one of the things, right? Notice that there's nothing in between here. These are very sharply defined. And that's because of destructive interference. The light really can only go through when there's exactly constructive interference. And there's so many other slits that if you're anywhere off of that constructive interference, you just get nailed by destructive interference. So these are all eliminated by all of the thousands of slits that are probably being illuminated, are destroying these secondary maxima. They just don't exist. Okay. I'm trying to think of what else they wanted to talk about. There's lots of things you can talk about. They're brighter because there's more slits to let the light through. The peaks are farther apart because the slits are closer together. Anyway, yeah, you just have to come up with three things. All right, let's see. The yellow light is made from two very similar wavelengths that produce two lines in the spectrum of sodium. Blah, 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 blah. This, evidently, of all of the diffraction grating resolvency questions, they've had two of these on the test. So we know how to do this, right? The resolvency R we never really calculate, but it's going to be like some number, right? Is the ratio of the wavelength to the smallest ability to discern, right? Okay, and then that's going to be the order times the number of gratings. So that's the number of slits. This is the order. This is what you're going to do for this is you're going to put the average of these two wavelengths in there. So find the average of those two and put the average. That's lambda bar. Just the bar just means average. Okay. And then for the this is going to be the difference, right? So subtract this guy from this guy and get the difference in wavelength. Okay. Now this you can average those two. You can subtract those two. We know, what do they say? The second order spectrum. Okay, so that's going to be 2. We're going to put a 2 in there, right? Okay. And then what you want to do is you want to figure out how many slits, right? So figure that out. Figure out how many slits. You're going to have an answer for that, right? And then they don't say how many slits need to be illuminated. They say determine the beam width. Like, ooh, well, how do you do that? Well, every 600 of those you need is a millimeter, right? Yeah. Okay, so take that N divide by 600. That's going to be how far the width divided by 1 millimeter. Yeah, every 600 lines that need to be illuminated represent 1 millimeter. So figure that out. Figure how wide it's got to be. I think you just divide by 600, and then that's the width of the beam in millimeters. Anyway, happy hunting. Hope that helps.